Welcome. In our previous presentations, we have discussed about the utilization of solar energy in direct and indirect fashion. So in direct applications of solar energy, one of the major and commercially successful application is solar photovoltaic. Solar thermal applications we have discussed in details in my previous presentations. Now in this session, we are going to learn about solar photovoltaic utilization of solar energy. Solar photovoltaics. Solar photovoltaics involve direct conversion of solar light into electricity. This is the snapshot of photovoltaic cells which are arranged in an array. In 1839, Edmund Becquerel, a French physicist, he first observed the photovoltaic effect and is credited with the discovery of the photovoltaic effect. Photovoltaic effect is the operating principle of the solar cell. Becquerel, at the age of 19, was experimenting with his father in his laboratory. He created world's first photovoltaic cell. In his experiment, he coated silver chloride or silver bromide on the platinum electrodes. Those electrodes were illuminated, and when those electrodes were exposed to illumination, voltage and current were generated along the electrodes. So because of this work, the photovoltaic effect has also been known as Becquerel effect. So this was the first experimental observation of solar photovoltaic effect. The theoretical basis to the photoelectricity or photovoltaic effect was given by Albert Einstein. As a part of his development of quantum theory, Albert Einstein published a theoretical explanation of the photovoltaic effect in 1904. But at that time, all the scientists rejected the proposal. They refused the proposal of the theoretical basis of photoelectricity or photovoltaic effect. But subsequently in 1919 or 1920, some scientist called Robert, he experimentally proved the theoretical basis of photovoltaic effect. Then Albert Einstein got the Nobel Prize for photoelectricity in 1923. So this is the story of photovoltaics. Solar cells developed in those days, like in 1940s and 50s, they were having very less efficiencies in the range of 1 to 2% only. And they were expensive too. So initially the application of photovoltaic cells was restricted to space applications. So only light and accurate applications were using photovoltaic cells. Subsequently, the energy crisis of 1970 happened, and also the cell efficiency improved, and there has been a remarkable reduction in the cost of the cell. So these events led to an accelerated development in solar photovoltaic technology. Today, solar photovoltaic power generation is one of the most commercially successful and widely used renewable energy technology. Talking about the benefits or advantage of solar photovoltaic technology, this technology makes use of the most abundant and free energy source on the planet, that is sun. So this is the first benefit. Now, direct conversion is possible with solar photovoltaic technology. No intervention of any heat engine or rotating equipment is required, because as in thermal power plants, a turbine and all the mechanical all the array of mechanical equipments is needed. Here those equipments are not needed. Third is no moving parts are involved in the utilization of solar photovoltaic effect. So therefore, the photovoltaic systems have minimal cost of maintenance with long life. The life can extend up to 25 years. So due to the minimum maintenance cost and long life, the reliability is also high. Then clean and silent source of power. It is a clean and silent source of power. It doesn't produce even any sound. So there is no sound pollution and environmental pollution involved with the utilization of this technology. Photovoltaic systems can be built in any size ranging from milliwatt to megawatt. Then the systems are modular, that more panels can be added as the demand increases. We can go on adding the number of panels to increase the output. Then SPV systems, that is solar photovoltaic systems, can also be set up as standalone systems. This is particularly useful for meeting the power needs, electrical power needs of islands which are remotely placed from the main grid. So these are the advantages of photovoltaic technology. These advantages make the technology very popular and convenient to utilize. Let us now focus on the fundamentals before we move over to the systems and design. It is essential to have some idea about fundamentals. So a material or device that is capable of converting the energy contained in photons of light. So the light contains photons of light into an electrical voltage and current is said to be photovoltaic. A photon with short enough wavelength and high enough energy can cause an electron in photovoltaic material to break free from the atom that holds it. Now here the short enough wavelength will be explained in the course of time when we take an expression, when we see an expression for the band gap energy. There the short enough wavelength will come. Next, with a provision of electric field, the movement of electron can cause flow of electric current. So the driving force to power photovoltaics comes from the sun. Photovoltaics use semiconductor materials to convert sunlight into electricity. So starting point for most of the world's current generation photovoltaic devices is the pure crystalline silicon. Now the atomic structure of pure crystalline silicon is like this. It has 14 protons, atomic number is 14 at the nucleus, and then 14 orbital electrons. So the outer orbit of the silicon contains 14 electrons. So it is multiple orbit atom. So here there are two in the first orbit, there are 2 electrons, then there are 8 electrons in the second orbit, and then there are 4 electrons. These 4 electrons in the spinning in the outermost orbit are called valence electrons. So the valence electrons are shown here in the simplified atomic structure. Now these valence electrons are more attached to the neighboring neighboring atom. So they are attached with the covalent bond. So in 3 dimensions, the atoms are the valence electrons are bonded to the other atoms. So each silicon atom forms a covalent bond with 4 adjacent atoms in 3-dimensional tetrahedral pattern. Now coming to a property of the silicon. At absolute zero temperature, silicon is a perfect insulator. There are no electrons free to roam around as there are in metals. Metals have free electrons. Due to the presence of free electrons, metals become good conductor of heat and electricity. But in semiconductors, as the temperature increases, some electrons will be given enough energy to free themselves from their nuclei, making them available to flow as electric current. So conductivity of silicon increases with temperature. This property of silicon is made use of to make the temperature sensors called thermistors. Those are accurate temperature sensors which sense the change in the temperature of a surface. Valence and conduction bands. Atoms consist of nucleus and electrons that orbit the nucleus. According to quantum mechanics, electrons of an isolated atom can have only specific, discrete or quantized energy levels. In elements that have electrons in multiple orbits, the innermost electron have the minimum energy. So we'll go back. The innermost electron have the minimum energy and therefore require a large amount of energy to overcome the attraction of the nucleus and become free. When atoms are brought close together, the electronic energy of the individual atoms is altered and the energy levels are grouped in energy bands. In some energy bands, electrons are allowed to exist, and in other energy bands, electrons are forbidden. The electrons in the outermost shell are the only ones that interact with other atoms. This is the highest normally filled band which corresponds to the ground state of the valence electrons and is called the valence band. The electrons in the valence band are loosely attached to the nucleus of the atom and therefore may attach more easily to a neighboring atom. So in this they give that atom a negative charge and leaving the original atom as a positively charged ion. Some electrons in the valence band may possess a lot of energy which enables them to jump into a higher band. These electrons are responsible for conduction of heat and electricity. This band of energy is called conduction band. The difference in the energy of an electron in the valence band and the innermost shell of the conduction band is called the band gap. So this slide shows three energy band diagrams. First is for insulator, second is for conductor, and third is for semiconductor. So quantum theory distinguishes between conductors, that is metals, insulators and semiconductors. In insulators, the valence band is filled, but the forbidden gap, so there is a wide energy gap. So the forbidden zone is wide in insulators. So the electrons from valence band, they cannot go to the empty conduction band. The conduction band is empty. So with whatever supply of energy, with whatever supply of stimulus, these electrons cannot move to the conduction band. That's why these materials are insulators. So materials whose valence gap is full and whose conduction band is empty, they have very high band gaps and are called insulators. No current can be carried by electrons in the filled band. The energy gap is so large that under ordinary circumstances, a valence electron cannot accept energy since the empty states in the conduction band are inaccessible to it. The band gap in these materials is greater than 3 electron volt. So the band gap in the insulator is greater than 3 electron volt here. Now materials that have relatively empty valence bands and may have some electrons in the conduction band are called conductors. So here the band is filled here. The valence band and conduction band, they overlap each other. So electrons from valence band with slightest stimulus, with slightest supply of energy, the electrons immediately move from valence band to conduction band. So this type of material readily conducts heat and electricity. So these are conductors. So in this case, the valence and conduction band overlap. These are metals and these are metals and they conduct heat and electricity readily. Now the third case is semiconductor. Here the forbidden zone or the energy gap is small as compared to the insulator. So, and the valence band is almost filled. So with slight stimulation, with slight supply of energy to the electrons, electrons can jump. When the threshold of energy is exceeded, the electrons jump from valence band to the conduction band. They begin conducting electricity. But for this, supply of some stimulus or supply of some energy, some form of energy is needed. This is the characteristic of semiconductor. In normal case, they are not conductors of heat and electricity. So materials with valence gap partly filled have intermediate band gaps and are called semiconductors. The band gap in these materials is less than 3 electron volt. So the band gap here is less than 3 electron volts. There are two types of semiconductors. One which are pure ones called intrinsic, and other which are doped with small amount of impurities called extrinsic semiconductors. Let's discuss about N-type material and P-type material. In semiconductors, if doped material has more electrons, the valence gap, if doped material has more electrons in the valence gap, then the doped material is called N-type semiconductors. N-type semiconductor is electronically neutral but has excess electrons. So this is obtained when silicon atoms are replaced with arsenic or antimony. This forms electrons that move around the crystal. If these excess electrons are removed, the atoms will be left with positive charges. So here this doped material has excess electrons. So if these excess electrons are removed, the atoms will be left with positive charges. So N-type material becomes positively excess positive charge. P-type material is something which is when doped material, when the P-type material is that in which the doped material has fewer electrons in valence gap. The doped material is called P-type semiconductor. So the P-type semiconductor is electronically neutral, but it has positive holes. Positive holes means missing electrons. So there is a vacancy for electrons in its structure. So these holes can accommodate excess electrons. This is obtained when silicon atoms are replaced with gallium or indium. This forms holes that move around the crystal through diffusion or drift. P-N junction. When P-type and N-type conductors are joined together, the excess electrons from N-type jump to fill the holes in P-type, and the holes from P-type diffuse to the N-type side, leaving the N side of the junction positively charged and P side negatively charged. So the negative charges of the P side restrict the movement of additional electrons from N side. However, the movement of additional electrons from the P side is easier because of the positive charges at the junction on the N side. Therefore, it is a one-way flow of electrons. It becomes one-way flow of electrons in P-N junction. Therefore, the P-N junction behaves like a diode, and it is therefore it is modeled like a diode only. So, in a P-N junction, N-type semiconductor is a donor while P-type semiconductor is acceptor. When a photon enters a photovoltaic material, photon of light enters a photovoltaic material, it can be reflected, absorbed or transmitted through. When this photon is absorbed by a valence electron of an atom, the energy of the electron is increased by the amount equal to the energy of the photon. If the energy of the photon is greater than the band gap of the semiconductor, then the electron will jump into the conduction band where it can move freely. Therefore, when a photon is absorbed, an electron is knocked loose from the atom. The electron can be removed by an electric field across the front and back of the photovoltaic material with the help of p-n junction. If the photon energy is smaller than the band gap energy, then the photon will only heat the cell. The result will be increased temperature of the cell. It will not excite the electron, and the electron will only move vigorously with higher kinetic energy. Due to special composition of solar cells, the electrons are only allowed to move in a single direction. So this figure shows the schematic of the p-n junction and a cell. So this is a n-type silicon and this is p-type silicon. This is a junction, p-n junction. When photons in sunlight, they strike the surface of a cell, the electrons are generated, electrons are excited, and they start moving towards this side up, and then electric current is generated. Similarly, from p-type, holes start drifting. So this is a positive charge, and then there is a potential difference generated due to this junction. So an array of solar cells called module converts solar energy into a usable amount of direct current. So the electricity generated by a solar photovoltaic cells is DC type. It is a direct current type electricity. This is a snapshot of a solar cell. This is a solar cell. Then solar cells can be assembled to form a module. So this is a module. You can see here, this is a module. And the modules arranged or installed in rows and columns is an array of modules. This is called a photovoltaic array of modules. Now coming to the discussion on the band gap energy. As we say, the photon need only have greater energy than that of a band gap energy to excite an electron from valence band into conduction band. Okay, so the solar frequency spectrum approximates a black body spectrum at about 5800 Kelvin. As such, much of the solar radiation reaching the earth is composed of photons. So solar energy is very much suitable to be utilized in photovoltaics. So these high energy photons will be absorbed by the solar cell. But the difference in energy between these photons and the silicon band gap is converted into heat via lattice vibration rather than usable electrical energy. So the expression for band gap energy is this. Band gap energy is equal to H is the Planck's constant and nu is the frequency. Frequency can be written in this expression as speed of light meters per second by wavelength of the light. Okay, wavelength. So band gap energy is expressed in electron volt. 1 electron volt is 1.6 into 10 raised to minus 19 joules. Planck's constant is 6.625 into 10 raised to minus 34 joules second. Nu is the frequency. Speed of light is 3 into 10 raised to 8 meters per second. Now silicon, this band gap energy is a characteristic of a material. Now silicon has a band gap energy of 1.11 electron volt. So if you substitute the value of 1.11 electron volt here, H is known, this Planck's constant, C is known, speed of light. So lambda can be found out. Lambda is nothing but the wavelength. Now we can find out the wavelength. So this wavelength comes out to be 1.12 micrometer. Now what does this indicate? If the wavelength is less than, if the wavelength of light is less than 1.12, the band gap energy will be higher. If wavelength is higher than 1.12, the band gap energy will be less. So the band gap energy, so photons with wavelength 1.12 micrometer or less are only useful in creating electron hole pairs and generate electricity. So in this solar spectrum, the visible range starts from here. So a very good amount of solar energy, solar light, or we can say the solar energy has a visible component, and lot of energy we can make use of to convert into electricity. Now equivalent circuit of a solar cell. This is a schematic symbol of a solar cell, and the solar cell is modeled as a diode. An ideal solar cell may be modeled by a current source in parallel with a diode. So this is a current source with the help of a photon generated with a photon, and then this is a diode. A shunt resistance and a series resistance component are therefore added to the model to make it more practical model. So the characteristic equation of a solar cell we will derive. The current produced by solar cell is equal to that produced by the current source, it is called photocurrent. So IL minus ID, the current flowing through the diode, and ISH, the current flowing through the shunt resistor. Now this is the current, I is the current flowing through the terminals here at the load. This is I. This is series resistance. This is shunt resistance. Current flowing through the shunt resistance, current flowing through the diode. V is the voltage across the cell terminal. So the current through these elements is governed by the voltage across them. Vj. Vj is equal to V plus IRS. Vj is the voltage across the diode, voltage across the terminals, I is the output current, and RS is the series resistance. Now this we can make use of. The current Shockley diode equation is given with this expression. ID is equal to I0. Current flowing through the diode is this. So I0 exponential QVJ upon NKT minus 1. So I0 is the reverse saturation current. N is the diode ideality factor. Generally it is 1. Q is the elementary electronic charge, which is 1.602 into 10 raised to minus 19 joules per volt. K is the Boltzmann constant, which is equal to 1.381 into 10 raised to minus 23 joules per Kelvin. T is the absolute temperature of the cell. At 25 degrees Celsius, KT by Q is 0.0259. By Ohm's law, the current diverted through the shunt resistor can be written like this: ISH is equal to Vj upon RSH. So this Vj can be substituted here, V plus IRS, and then the expression can be written like this: I is equal to IL minus the diode equation, and then V plus IRS upon RSH. Generally, the series resistance is very small as compared to the load resistance, and shunt resistance is very large as compared to load resistance. So these are neglected. So these terms can be neglected. So this is having very high denominator, and this is having very low numerator. So IRS term and this term can be neglected, and the characteristic equation of a solar cell becomes this: I equal to IL minus I0 exponentially QV upon KT minus 1. Now if the terminals of the cell, photovoltaic cell, are kept open, then current flowing will be 0 and the voltage is maximum across the terminals. So that voltage is called open circuit voltage. So this can be numerically obtained when we substitute here equal to 0, I, current flowing through the cell is 0, and then find out the value of V, that will be VOC. So open circuit voltage. Open circuit voltage becomes the characteristic of a photovoltaic cell. Similarly, if these terminals are shorted, connected to each other, then voltage will be 0 and current flowing through the circuit, current flowing through the cell will be maximum, that will be equal to short circuit current. So in that case, that will be equal to photo generated current. So short circuit current is the maximum current that is generated by the cell. So VOC, open circuit voltage, and short circuit current become the characteristic of the photovoltaic cell. Now if for different values of V, if we find out corresponding values of I, and then we plot on this I and V diagram, then for different values of V, we will get different values of I, and this a characteristic curve of a typical solar cell corresponding to a given irradiance, solar radiation intensity IT, and a fixed cell temperature TC is obtained. So this figure shows a typical characteristic of a solar photovoltaic cell. Between now at short circuit current, when the cell is operating at short circuit current, it doesn't deliver any power. because voltage is 0. Similarly, at open circuit voltage condition, again it delivers 0 power because current is 0. But between open circuit and short circuit conditions, the power is greater than 0. So power is delivered by the cell over these operating conditions. So the load characteristic is a straight line with slope 1 by V, that is equal to 1 by. So this is a load characteristic. Corresponding load resistance, if it is given, then this indicates the load operating point of the cell. So if the cell operates with the small load resistance, then the operation will be in this AB region. So the cell behaves as a constant current source if the load resistance is very small. If the load resistance is large, then the cell will operate as a constant voltage source. It operates in a DE range. Now if we connect a variable resistance load across the cell and then go on changing the resistance so that a maximum power, the point of maximum power can be located. So corresponding maximum power will be obtained corresponding to optimum resistance. So this point is called, at which the maximum power is obtained, is called a maximum power point. This maximum power point corresponds to delivery of maximum current by the cell and maximum voltage by the cell. So the maximum power is nothing but a product of I max into V max. Now this is the area under the curve. This is the power delivered by the cell, and the maximum power that the cell could deliver is the product of ISC into VOC. So this becomes a benchmark of the maximum power. If we compare this benchmark with this delivered power, we can introduce a factor called fill factor. So fill factor is nothing but the ratio of the maximum power delivered by the photovoltaic cell by the theoretical, or we can say imaginary maximum power the cell would deliver with ISC and VOC. So this is a fill factor. Fill factor is a very important parameter in the performance of a solar cell or solar photovoltaic module. Now temperature of the cell can be evaluated using this expression. T cell is equal to T ambient temperature plus NOCT. NOCT is the nominal operating cell temperature minus 20 degrees into solar radiation intensity for that location divided by 0.8. So with this we can find out the temperature of the cell, and then we can always correct the power delivered by the cell. The more discussion will happen when we discuss about the during the design of the system design of photovoltaic cells or photovoltaic modules. So adding modules in series increases array voltage, while adding modules in parallel increases array current. Current generated increases almost in linear fashion with solar radiation, while voltage increases slightly with ambient temperature. These characteristics we will study in detail when we discuss design. The output power from a photovoltaic cell is given as power is equal to current into voltage. So if we introduce resistance, then the power expression becomes I square R. Now substituting these characteristics in the original equation, power is equal to IL minus I0 exponential QE upon KT minus 1 into V. So this is the power delivered by a cell. Now efficiency of the cell or module can be evaluated with this expression. Maximum efficiency is the maximum power delivered by the cell or module divided by area of the cell or area of the module, surface area, into solar radiation intensity on the tilted surface, watt per meter square. So here we will stop in the first part of the fundamentals. In the next session we will cover the practical aspects of solar photovoltaic cell and system design. Thank you.